Hi, I'm Mistress J, and these are your Commerce Exam Nuggets, Lesson Number 6, Documents of Local Trade. Now before we begin, here are a few items I need you to get. A pen or a pencil, a notebook or device, and your thinking cap. Now let's take a quick look at our objective for today. Before we begin, let's quickly recap our last nugget, local trade. Here's the definition: the exchange of goods and services within a country through retailing or wholesaling. And when we have local trade, we use a number of documents to record those transactions. And that's what we're looking at today, local trade documents. Let's suppose I was a consumer and I wanted to find out who was the best wholesaler in terms of prices. I would write a letter of inquiry to both wholesalers, asking them for a list of prices and their goods. In turn, those wholesalers would give me a documentation called a quotation with the list of their best prices and goods. I would then make a decision of which wholesaler. Once I've chosen the wholesaler I want to go with, I place an order with him. In turn, he gives me a document known as an acknowledgement to confirm my order. The wholesaler then packages my goods and sends an advice note to let me know your goods are on the way. Once the goods are on their way to being delivered, a document known as the delivery note is sent with it. That is so that I, as the consumer, can confirm that everything I ordered is in the delivery. The wholesaler then discusses how much I owe through a document known as the invoice, followed by a statement of account to show how much I owe for the period of time. Once I've checked both of those documents and made sure there's no mistake, I then write a check to the wholesaler. He in turn gives me a document to prove my payment. So let's recap those documents. Can you remember the documents that were sent from the buyer to the seller and the seller to the buyer? Great! Wow, it's just that simple. I would like to thank you for watching, and remember, with God, virtually anything is possible.
So for today's lesson, we will be continuing with laws of indices. And we are going to look at a new law today. Okay. So our objectives for this lesson are going to be to identify and apply the negative laws of indices. And we are going to demonstrate how to simplify expressions by applying the correct law of indices. And once again, for those of you that are new, I would say stay in the lesson and learn what you can learn about these particular laws. But if you missed the first set of laws that we did, the recordings and resources for those previous lessons can be found on the virtual learning website, so you can check them out on your own free time. So a quick recap. Let's see who remembers some of the laws that we started to look at. So which laws of indices can be applied to simplify this particular expression? And you can type your answer in the chat box. You don't have to simplify the expression, just let me know which set of laws of indices can be applied to simplify this expression. So here's the expression on the screen. So based on the laws that we've covered already, which ones do you think would apply to this particular expression? Okay, I'm seeing some answers come in, and I will give you a hint. Laws there is plural, so there's more than one law. Okay, I'm seeing some answers. Okay, so for those of you that did respond, most of you are correct. So let's see what our laws are. Okay, so the laws of indices that can be applied to simplify this expression is the power of a power law along with the division law. So these two laws are quite evident inside this particular expression. And so we're not going to simplify this one, but there will be examples similar to this at the end of the lesson. So if you got those right, kudos to you. So now let's look at negative exponents. So just another little recap. We know that 2 to the power of 2 or 2 squared means 2 times 2, which is equal to 4. We know that 2 to the power of 1 would just be number 2. And we know that 2 to the power of 0, or anything to the power of 0 that is not 0, is equal to 1. So now, what do you think 2 to the power of negative 1 means? Does anybody want to take a guess? You can type your answer in the chat box. I'll wait, let's say 1 minute to see if someone can actually guess to see what's going on before we actually do it. Okay, I'm seeing some answers come in. Okay, I actually see the correct answer somewhere. Let's see. Okay, I'm seeing some correct answers. So for those of you that are just guessing, good job. Some of you are actually making some educational guesses. But I actually see some of the correct answers. So let's see for those who are correct. So what does 2 to the power of negative 1 mean? So we cannot really leave an exponent negative because there is no way to really express its meaning. So therefore, I must make this negative exponent a positive. And here's how we do that. No, you don't have to write this. We change it into a fraction, or we do the reciprocal of what 2 to the power of negative 1 means. So for those of you that answered 1 over 2, you are actually correct. So before I actually show you the correct law, let me go back to the other slide, the first slide, like this one. So if you notice, there's a pattern going on here. I don't know, some people picked it up, but some people may have. There is a pattern. For every time our exponent decreases over here, so we went from an exponent of 2 to 1 to 0 to negative 1. Over here, if you would notice, the final answers that we got when we multiplied 2 to the exponent, the answers were actually decreasing as well. And so the answers were actually decreasing by 2 or being divided by 2. So from 4 to 2, if we divide this by 2, we're going to get 2. If we divide 2 by 2 again, we're going to get 1. And so therefore, this is one of the ways that they justify why 2 to the power of negative 1 is 1 over 2. If we take this 1 and continue the pattern and divide it by 2, we will end up with 1 over 2. And so this will work for any number that is not 0. If we had 3 to the power of 2, the numbers on, or the answers to the expression would be continuously being divided by 3. And so 3 to the power of negative 1 would be 1 over 3. So that was just one of the fun ways that people justified or proved why 2 to the power of negative 1 is 1 over 2. So let's get back into the actual law and some examples. So let's watch a YouTube video. And this video, the link I will post inside the chat later. And this is another video that's going to help you understand why we use the reciprocal.
Thank you again for joining me on this lesson where we are going to explore the properties of negative exponents. But first, let's reactivate what we already know about positive exponents. For example, 5 raised to the second power. We know that this is equal to 5 times 5. Another way to look at this is calling it 5 squared. And we also know that 5 times 5 is equal to 25. And that's pretty easy and something that we should be familiar with. But what if that exponent was a negative 2 instead of a positive 2? When we think of negative or the word negate, we think of it as performing the opposite or inverse operation. So with positive exponents, our operation is multiplication. So what is the inverse or opposite of multiplying? You were correct if you said divided. So in this case, we are going to express as a fraction that 5 to the negative second power is equal to 1 over 5 to the second power. Notice how we threw away the negative sign in the exponent. Let's see that again one more time. And since we know that 5 squared is equal to 25, we can conclude that 5 to the negative second power is equal to 1/25.
So this video just proves another way how the negative exponents work. So with the first way or the first proof that I just showed you with the pattern is that we continue to divide by the actual number. And that's how you would figure out whatever the negative power is, how you would get the answer. And so this video basically just justifies the division aspect of it. So like he said in the video, we know that when we have a positive power, that number tells us how many times we're going to multiply the base. And so now when we have a negative power, that basically just tells me how many times I'm going to divide the base. And so basically, positive and negative are opposites. So if we had a positive power, we do multiplication. But if we have a negative power, we would do division. And so it would be the same thing as writing the reciprocal. So let's look at the actual rule. So for any integer n, a to the power of negative n is the reciprocal of a n. And so here in the box is our actual rule. So whenever we're given something that has a negative power, and in this case, like stated, n would be an integer, we just write the reciprocal. So we put it under 1. This now becomes my denominator, and my exponent is no longer negative. So the number will still remain the same, but it will no longer be a negative number. So this you can write down. This is our rule for negative exponents. So whenever you have a negative exponent, you do the reciprocal and your exponent will change to a positive. And if you can simplify, then go ahead. So now let's look at some examples. So once again, we do not want to have negative exponents in our answer. So we get rid of the negative exponents by flipping the exponent over like reciprocals. So if the negative exponent is on the top, we move it to the bottom. And we know that if we write anything over 1, it's still the same thing as a whole number. And so this would be a simplified version for this. And so if the negative exponent is to the bottom, you move it to the top. So if you have an example where you're given a negative exponent to the bottom, you still do the reciprocal, meaning to flip this fraction, and it will now go to the top, and your negative will become a positive. Okay, so I'm seeing someone ask, why would the power go to the denominator? So the power is going to the denominator because the rule says that we do the reciprocal and we're dividing. So that's why the power would go to the denominator. So this, you don't have to write this. This just helps you understand reciprocal. And all reciprocal means is to flip a fraction in the case of math. So let's look at another example. If we're given -5 all raised to the power of -2, we flip the fraction, or we do the reciprocal, because we know that anything you can change into a fraction by just putting it over 1. And so we just do the reciprocal. And once we do the reciprocal, our exponent will now become a positive exponent. And if you can simplify further, like in this case, we could. And so -5 squared would be 25. So our final answer would be 1/25. It's not stated here, but you can write it in if you're writing this down. Okay, let's move along. So a negative exponent is an inverse. So as seen with the rule, likewise, if we have a letter or variable, we still do the same exact thing. It's just now that with this particular example, we can't really simplify any further because we don't know what x is, but the same rule still applies. So let's look at some examples with just numbers. And then we'll do some examples with variables, and then we'll do some mixed examples. So we have 3 to the power of -1. So therefore my answer is going to be 1/3. And if you remember from previous lessons, the power on my 3 is still 1, but we know that if we have a power to 1, we don't really have to write the 1. Or we would say that the 1 is silent in a sense. Okay, let's look at number 2. We have 4 to the power of -2. So I'm going to write the reciprocal of this. The rule tells me to put 1/4 to the power of 2. And I can simplify this further to be 1/16. Let's move on to number 3. We have 5 to the power of -2. So applying the rule, I'm going to have 1/5 to the power of 2, and this simplifies to 1/25. Now to put a pin in here for number 3, If you noticed on one of the last examples that we did on the previous slide, where we had -5 raised to the power, the reason that the answer was still 1 over 25 is because of the rules of integers. We know that if you square -5, which will mean -5 times -5, we know that a negative times a negative will give us a positive. And so that's why these two answers would be the same, just in case if anyone was wondering. And let's look at our final example, 6 to the power of -2. So I'm going to have 1 over 6 to the power of 2, and my final answer is going to be 1 over 36. Okay, let's move to the next slide. So this particular clip is now, it was a continuation from the first video. However, I cut it so this part of the examples won't get mixed up with the first set. So now we have where our laws of indices are now being combined. And so here is an example of where two laws of indices are combined, and there would be multiple ways to do this, but this particular video only shows one way. So let's watch the video.
So now we can apply our understanding of negative exponents to an example where we want to simplify the expression 2 to the -8 power multiplied by 2 to the +5 power. Exponents with the same base. We know that there's a rule, and that rule is that we can add exponents together. In this case, -8 plus 5 is equal to -3. So now we have 2 raised to the -3rd power. And we know that since our exponent is negative, that we can rewrite this as 1 over 2 to the 3rd power. Again, we remove the negative sign. We also know that 2 to the 3rd power is equal to +8. And if you include that, 2 to the -3rd power is equal to either 1 over 8 or 0.125. Now, there are different ways to tackle a problem like this that will still get you to the same correct answer. So I'll leave you with a question, and that is, could you have simplified this expression using a different strategy?
Okay, so that was just another example of where the negative law is combined with another law. And in this particular example, the law that it was combined with was the law of multiplication. And so at the end of the example, he asks a question: could you have simplified this expression using a different strategy? And in this case, the answer is yes. We know that there's always more than one way to do almost basically anything in life. And so the same thing applies here. In this case, if we go back to the beginning, some of you may have noticed that, hey, we have a negative power. And so some of you may have applied the negative law here, which would have been 5 steps, would have been a little different. So yes, it really doesn't matter which way you start as long as you can justify what you did. So that was just another way of explaining. But the best way would be to go the shortest route. And in this case, the shortest route would have been to apply the multiplication law first and then apply the negative indice. So on your own time at home, you can write this down and you can try the different ways of solving this expression or simplifying this expression. And I just gave you the different way, which would be to use the negative law first, and then you can determine which law will come after that. So let's look at some other examples where we have more than one law of indices that can be applied to an expression. So we're going to try for these 4 different laws of indices, And so this is where you can write. I'll go through the steps with you. And so we will now see the different laws applied to one particular question. So our first example, we have a to the power of 5 all to the power of -1. In the chat, type and tell me which law of indices can be applied to number 1. Let's see if you can see it right away. Okay, I'm seeing some answers. So which two laws would be used to apply to number 1? Okay, excellent. So I'm seeing the power of a power law as well as the negative law. So as long as you are able to identify these laws right away, then you know which laws would be correct to apply. Now, as stated in the previous slide and in the previous example, once you have identified the laws that are used, it really doesn't matter which laws you use first, as long as you use them correctly and they apply to the expression. But for the sake of this lesson, I went the shortest route. And so in this case, we can apply the negative law first. And basically, that's it, because in this case, we don't know what A is, so we can't simplify any further. So our final answer is just going to be 1 over A to the power of 5. Very good. I see some people actually answered the question. So now, if you wanted to use the power of a power law, if you remember, the power of a power law states that you can multiply the powers. And in this case, if we multiply the powers, we would have had A to the power of 5 times -1, which was still going to give me A to the power of -5. And then we know that we can then apply the negative law and we would still end up with this answer. Do we have any questions? If that was clear, you can type yes or send a thumbs up in the chat, please. Very good. Let's move on to example 2. Which two laws can be applied to example 2 here? You can type the answers in the chat box. So number 2 is y squared times y to the power of -4. So which two laws can be applied here? Okay, I'm seeing some answers, seeing some correct answers. Very good. I actually see a correct answer. So let's look into it. So I see a multiplication sign here, and then I also see two things being multiplied that have the same base. So with that being said, the multiplication law is one of the laws that can be applied here. And then if I look at the exponents, I see a negative exponent. So that means that the negative law can also be applied here. So once again, I'm going to take the shortest route. We can apply the multiplication law first. And what does the multiplication law state? Can someone type that in the chat box for me? If you remember, when we have the same bases that are being multiplied, what do we do with the exponents? Let's see who remembers. And let's see who will be the first person to answer. When we're multiplying with the same base, what do we do with the exponents? Very good. I think this is Bernardo. He was the first person to answer. Yes, so we add the exponents. So let's see how it looks. So we add the exponents. So we have 2 plus -4. And we know that based on our integer rules, when we are adding a negative number, that really means that we are going to subtract. So our next line is going to be y to the power of 2 take away 4. And therefore, we are going to have y to the power of -2. And once again, because we have a negative exponent, we can apply the negative law of indices and do the reciprocal. So my answer is going to be 1 over y squared. And so this is my final answer. We can't simplify anymore because we don't know the value of y. Any questions? If it was clear, you can type yes or send a thumbs up. Very good. Let's look at number 3. Okay, so just a quick clarification back to number 2. We want to make sure to not confuse y to the power of 2 by itself with 1 over y to the power of 2. They're not the same. 1 over y to the power of 2 would be this fraction represented here. But if you just have y to the power of 2, y to the power of 2 as a fraction would be y to the power of 2 over 1. So there's a difference there. So be sure not to confuse the two. Okay, let's look at example 3. So now example 3, we have a negative exponent as well as we have division going on here. Now with this particular case, I would suggest that you start with the division law first, because this negative exponent, if you notice, this negative exponent does not apply to the 36. This negative exponent is only on my h term. So 36 and h are 2 separate terms. Now, if you remember when we were doing the power of the power law, in order for this -4 to be applied to the 36, this 36h would have been in brackets. So therefore, one more time, the -4 is only the exponent of the h. The exponent on 36 is actually 1. So in this case, the best case scenario is to do the division law first, where we take 36 and divide it by 9, we get 4. And then because we have 2 bases that are the same, we can go ahead and subtract the exponents like the division law states. When the bases are the same, you subtract exponents. So therefore, we're going to have -4 take away 4, as seen here. And so now we're going to have 4h to the power of -8. And so now we can go ahead and apply the negative law. So one more time, the negative law does not apply to the coefficient 4 here. The negative is only on the h. And so therefore, when we are writing our next step, remember that when we have a number and a letter together, or 2 letters together in algebra, we know that there is multiplication going on between there. So really this is saying 4 times h to the power of -8. So in this case, since our negative exponent only applies to the h, when I move to the further step, when it's time to do the reciprocal, I will only do the reciprocal on the h, not not the 4. So I'm going to separate them and actually show my multiplication sign. So this is going to be 4 times 1 over h to the power of 8. Please let me know if that was, well, we're not quite done, but please let me know if that was clear. And once again, if you have a question, you can ask your question in the question and answer feature. Okay, so I'm seeing someone asks, how did I get to -4 if we have +4? Remember, if you remember the division rule states that when we are dividing, we subtract the exponents. So this second symbol is subtraction. This doesn't indicate that it's negative. It's a subtraction. So therefore, we have -4 subtract +4. I hope that answers your question. Now, I hope you're not confusing it with number 2 when we did the multiplication. The only reason we subtracted these powers was because of the laws of integers. We did technically add them, but because our second exponent was a negative, that's how come this one turned into subtraction. So for multiplication, when we have the same basis, we add the exponents. And for division, when we have the same basis, we subtract the exponents. Great. So we can simplify this further. And if you remember how to multiply fractions, we can turn 4 into a fraction by putting it over 1, and then you multiply numerators and denominators. And so when it simplifies, we'll have 4 over h to the power of 8. And this is our final example, final step for this particular example. Okay, now let's look at number 4. So we have 5a to the power of 4, all to the power of -2. So now let's compare 36h to the power of -4. 1 second. Let's compare this first part here to this particular example. So what I was explaining earlier was, in this case, the -4 is only on my h value. It's not on 36. And I stated that in order for the -4 to be applied to the 36h would have had to be in brackets. And so number 4 is a perfect example of what I was talking about. This -2, based on the power of a power law, this -2 will be applied to every term inside the brackets here. So based on the power of power law, I would have 5 to the power of -2, as well as a to the power of 4 to the power of -2. So this is telling me that everything inside this brackets must be raised to the power of -2. Whereas over here for number 3, this is telling me that only h has the power of -4. So let's continue with this number 4 example. With this particular example, the 2 laws that can be applied here would be the power of a power law along with the negative power law. In this case, the easiest way to go would be to start with our negative exponent here. And so because we have a negative exponent, we're going to do the reciprocal. And so once we do the reciprocal, our exponent will change to a positive. And so it doesn't matter what you are raising to the negative power. Everything that you are raising to that negative power will go in the denominator. Not just part of it, all of it. So 5a to the power of 4 is going to go to our denominator. And now our exponent is positive. And yes, we can continue to simplify. This is not the final answer. So we can simplify our denominator by applying our power of a power law. And if you remember, that law states that everything that's basically inside the bracket, I must raise to this power of 2 by multiplying. So if you remember, each term, 5 is one term and a to the power of 4 is another term. So therefore 5 must be raised to the power of 2. And our power of power law states that if we have 2 exponents, we're going to multiply them. So this is the next line. So we're going to have 5 to the power of 2. And a to the power of 4 times 2 is going to give me a to the power of 8. And simplified further, my 5 to the power of 2 will simplify to 25. And so my final answer is going to be 1 over 25 to the power, 1 over 25a to the power of 8. And so once you take these questions step by step, they're not so hard. You have to identify the laws first, the correct laws that apply, and then you apply the laws step by step. Okay, so if it was clear, you can type yes or send a thumbs up in the chat. And if you do have a question about any of the examples here, please refer to the question and answer chat feature. Okay, I'm seeing some person say yes, very good. And so once again, these types of questions, you can only get them if you continue to practice, practice, and practice. So now, I'm going to copy and paste these particular links inside the chat, along with the link for the video that was shown if you want to rewatch. This first link here is going to give you some information on all the laws of indices along with some examples. And this second link here is the online quizzes game that you guys said that you like on laws of indices.
The Bahamas' coat of arms is a collection of elements indigenous and important to our country. The pretty pink conch shell at the top symbolizes the marine life of the Bahamas. The wavy green palms around it symbolizes the natural vegetation we possess. The Santa Maria flagship of Christopher Columbus appears on the shield of the coat of arms. Waves of blue and white represent the crystal clear waters surrounding the islands. The sun at the head of the shield signifies the bright, sunny climate we experience year-round. It also indicates the bright future of the Bahamas. A blue marlin, the national fish, and a flamingo, the national bird, support the shield. Forward, upward, onward, together. The national motto is at its base. Did you know that a national competition was held to produce the motto? The winners, Vivian Moultrie and Melbourne Bow, were both 11-year-old students. Hervis Bain, a renowned Bahamian artist, prepared the preliminary design of the coat of arms.